There's one more issue that can crop up on us, unfortunately, when it comes to tangent lines for polar equations. And that is tangent lines at the pole, at the origin. That can create difficulties. So suppose that we have a graph of r equals f of theta, and it passes through the origin at angle values theta equals alpha, right? So some alpha angles, it just goes through the origin, sort of like a flower curve, like this one. And the derivative at those alpha values is not equal to 0, because if the derivative was equal to 0, then we'd have problems. Then the tangent line to the graph of r equals f of theta at the pole is theta equals alpha. Now remember what this looks like. When you have theta equal to a constant, that is a diagonal line. Through the origin. Or through the pole. Now the slope of that line by definition would be the tangent of alpha, because it'll be, well, you'll see, it'll be over and up, so it'll work out, right? So this will be the tangent of that, will be that slope. We actually mentioned this as a special case right here. See, right? Tangent line is a diagonal line, right? And tangent of theta. So that's what this was talking about, but that's all they were going to say about it. So I think it's better to have the box on the next page. So back on this previous page, we could say see page 35, right? To give it a look, or whatever page it might happen to be in your course pack, but you get the general idea, right? Okay, so it's a kind of a special case. This is useful because it states that the zeros of r equals f of theta can be used to find the tangent poles, because the zeros, of course, will be where it goes through the poles. And then we can use that to find the tangent lines at those poles. Nice. Provided that the derivative is not also 0 there, because if the derivative was 0 there, we'd have problems. And since the polar curve can cross the pole more than once, it can have more than one tangent line to the pole. So look at this lovely rose curve, although it doesn't look much like a rose to me, it looks more like a daisy. But it has this lovely rose curve, and we're going to find the tangent lines in both polar and Cartesian form. Ooh, tricky. So we're going to do polar and Cartesian form for these tangent lines. Okay, so one thing I need to know right off the bat is what's the period, because I need to know how much I'm looking at here. So let me move this graph. I can actually close that last graph. I don't need it anymore. Oh, I can close that one too, I think, but here we go. All right, so if I'm swooping through this lovely curve, and remember the way that I do this is when I graph it, I say, hey, graph me 2 cosine of 3 theta, but make theta less than or equal to d. And then I can put in a slider bar for d, and I can watch it grow. And it looks like pi, right? Pi is our period. So we want to make a note of that somewhere else, right? Right away, kind of note that, because that means that we will restrict ourselves to that period. Oh, I should make it an interval. Technically, it's 0, comma pi, and with brackets. Okay. Okay, so now let's look at f of theta. F of theta is equal to 2 cosine of 3 theta. So if I want tangent lines at the pole, I would set it equal to 0, right? Because I'm finding the zeros. The zeros of this function will be places where the tangent line at the pole exists, right? So I'm going to set it equal to 0 because I'm looking for tangent lines at the pole. Right? That's why it's equal to 0. Okay, well, 2 has nothing to do with it. I could divide both sides by 2. That means that the cosine of 3 theta has to be equal to 0. Okay, so that means that my angle is 3 theta, right? So I have some angle. Now let's think about that angle. Don't worry about the 3 theta part. Just worry about the angle. All right, so the angle is 3 theta. What are some angles that have a cosine equal to 0? So if you think about your unit circle, for once I'm going to draw it, right? So on unit circle, where's the cosine equal to 0? Well, cosine is equal to 0 up top and down below, right? Pi over 2 and 3 pi over 2. right? And so on. Okay, so this would happen at pi over 2, obviously, 3 pi over 2 for sure. But we have to keep going because it's 3 theta, so I have to keep going around. So it's not, in other words, it's not just theta. So let's see, what's another one? So if I go up, back, top, that's 5 pi over 2. Up, back, down, that's 7 pi over 2. Up, back, down, that's a word. And then back to the top would be 9 pi over 2. To the bottom again would be 11 pi over 2. And I think we've got enough. Matter of fact, I know we do. Right, just keep going. Now 3 theta is equal to these. So what's theta equal to? Well, you multiply everything by a third, right? That'll get you your theta, right? So your angle is one of these angles, but that angle was 3 theta. So theta would be equal to, so take a third and multiply it by each one of these, right? Oh, I'm just going to leave the 3 theta there. I didn't want to cross it off, but that's what would happen. So the third and the 3 are canceling. So it'd be pi over 6, 3 pi over 6, aka pi over 2, right? Because 3 pi over 6 is pi over 2. 5 pi over 6, 7 pi over 6, 9 pi over 6, aka 3. 3 goes into that 3. 3 goes into that 2. So 3 pi over 2 and 11 pi over 6. Uh-oh. Hold on. This one, well, that one, and that one, you can cross them all off because they're not in the period. Right? See why it's so important to figure that out the first time? Right? So that means that I only want these 3 angles. I want pi over 6, which looks right there. There it is. There's your equation of your tangent line, right? So your polar tangent lines are really easy because the polar tangent lines, look what it says. It says theta is equal to that angle. So your polar tangent lines are theta equals pi over 6. Oh, I'll put them down here. Theta equals pi over 2, which is right here. And you can see it, right? It kind of cuts through that curve, but it only touches at the pole, right? And last but not least, theta equals 5 pi over 6, which is this line right here. There we go. Now I'd be done, except they want the Cartesian form also, the jerks, right? So I've got the polar lines, no problem. Polar lines are easy because the polar lines are whatever angle you came up with. So we had 3 angles. Those 3 angles are polar tangent lines, right? So this one is theta equals pi over 6. This one's theta equals pi over 2. And this one's theta equals 5 pi over 6. Done. All right, now we need rectangular forms. Okay, so let's think here. Well, I know all these things go through the origin, so I know it's all going to be just y equals mx, right? There's not going to be any b because, right, because they go through the origin, right? It'll just be y equals mx. So all I need to do is figure out the m, and I'm golden. All right, so let's go start with theta equals pi over 6. At theta equals pi over 6, m is, now look up, there's your m, right? This is m. M is the tangent of whatever angle you've got. So m is the tangent of pi over 6. Tangent of pi over 6 is, oops, I don't know what I'm doing with a comma there. It's the sine of pi over 6 over the cosine of pi over 6. Which luckily for me, we all memorized in pre-calc. So it's a half over the square root of 3 over 2, which would be 1 over the square root of 3. That means that y equals 1 over the square root of 3x. There's equation number 1. All right, let's do it again. So theta equals pi over 2. The slope is the tangent of pi over 2. Tangent is sine over cosine, which is 0 over 1. Oh, no, which is 1 over 0. Oops, my bad. I got all excited. Which is infinity, and you might think, oh, no, but that means that's a vertical line. And we know what vertical lines look like. I mean, look at it. You could have figured this one out without even doing anything. This was x equals 0. We know what vertical lines are. We've known that since Algebra 1. Last but not least, theta equals 5 pi over 6, which if you're paying attention, you can probably guess what this one is because it's related to the green one, the theta equals pi over 6. So it's the tangent of 5 pi over 6, which is the sine of 5 pi over 6, over the cosine of 5 pi over 6, which is 1/2 over negative square root of 3 over 2, which is negative 1 over the square root of 3. See what I mean? So that means that y equals negative 1 over the square root of 3x. There they all are in rectangular form. These are the rectangular equations of the tangent lines. They're the same lines. They're just writing it in two different formats. You're writing it in a polar format, which is easy, and a rectangular format, which is not so easy, but you can manage it. The beautiful thing is because they go through the origin, they're always just going to be the slope times x. So it makes it easy. As a matter of fact, we could write that up above. So if this is true, then the tangent lines in rectangular form, oh, I don't think I can fit the word rectangular. Rectangular tangents will always be y equals tangent of alpha times x. Always. Which is what we found just down here.